We're on our practice test C, objective 7. This is a distributive practice objective, so we will be working problems that we should be familiar with. So we'll go through one at a time and kind of just review each one of the concepts and work our problems together just to ensure you know that you have an A+ answer. Reading for the first one, it's simply asking us to find a density of a gas. Nice little words there, says standard temperature and pressure. So we're at STP, and the gas we're looking to solve for is fluorine, one of our lucky 7 molecular compounds. So practice test C, this is objective 7. Question number 1, we know density at STP can be found just very readily by taking the molar mass over our standard molar volume answer. Whoops, misspelled already. So molar volume. The gas we were given was molecular fluorine, one of our lucky 7 diatomic molecules. So again, its molar mass is 38 grams in every 1 mole. So real and easy, 38 grams in every 1 mole set over that molar volume of 22.4 liters, and we find a density. 38, hit with me please, just to be sure I don't make a calculator mistake. 38 is the molar mass divided by the molar volume of 22.4, and I get a density 1.696, let's do a little rounding, 1.70 grams per liter of fluorine. Now remember, this formula only works at STP. If you are in other conditions, non-standard conditions, density formula is in a previous objective, involves the ideal gas law. So just a reminder, this works at STP. Let's go on. Whoops, number 2 reads, let me find it. Hydrogen gas reacts with ethene to form ethane, and we have a combination reaction. Now this is the same equation from practice test to practice test, so that should be coming pretty readily for us. Writing out our balanced equation shows the molecular form of hydrogen, H2, combining with a molecule called ethene, C2H4. The pattern of change is a combination, and we simply add on 2 more hydrogens to this organic molecule, and we've produced something called ethane. So our balanced equation shows a 1:1:1 stoichiometric ratio, so can't get any easier than that. We are given the limiting reagent when we have 100 grams of this reactant called ethene. We're going to react it with 15 grams of molecular hydrogen. We'd like to know the maximum yield of our product, and part C will ask us how much excess reagent is left over. So we have 2 story problems to work out. If indeed 15 grams of hydrogen limits the reaction, we'd have our 3-step stoichiometry problem where we will divide, we'll ratio, we'll multiply, where the target is C2H6. We have 100 grams of ethene, C2H4, and I'll get those parentheses ready as well, where we divide, we ratio, we multiply, knowing now C2H6, the same target. So in the heart of our problem, we have the want over given ratio. In our first conversion, we take the molar mass of hydrogen to convert it into a mole. 1 mole of hydrogen has a molar mass of 2 grams. We stated that we couldn't be any happier with our 1:1 stoichiometric ratio. For every 1 mole of product that forms, 1 mole of hydrogen was consumed. The molar mass of our product, I know carbon weighs 12, but there's two of them. Hydrogen is 1, but I count 6, so 24 and 6 gives us a molar mass of 30 grams for our product called ethane. Number, unit, label each time. I'll get this guy ready as well so we can just get our calculator going once. We know that C2H4, its molar mass gave us the 28 grams per mole. Still a nice 1:1 molecular ratio here. 1 mole of C2H4 is used for every 1 mole of the ethane that's produced, C2H6. Same molar mass as we have the same target, of course. So here we have our parentheses set. Let's grab our calculators. If indeed 15 grams limits the reaction, we can calculate by hitting 15 divided by 2 times 30. It's a key sequence to pull that out. $15 divided by 2 times 30. I was just checking my work. I found 225 grams is my first answer. Let's hit for the second row. 100 divided by 28 times 1 over 1 times 30. Did you get the same thing I did? 107.14 grams. And this one was an even, so 0.0. Of course, we understand that we can only make as much as our smaller answer, so please be sure you are indeed labeling your maximum yield, max yield, the smaller of our two answers. We want to identify the reactant that gave us the smaller answer as our limiting reagent, and therefore we know hydrogen must be in excess amounts. Well, how much excess do we have? Knowing that hydrogen is in excess amounts, we're being asked to calculate how much of that did we actually waste or put in extra for. In the third step, we're going to start our stoichiometry problem with the limiting reagent, that 100 grams of the limiting reagent called ethene. And now all of a sudden we're going to target not the product like we did up above, but we're going to go to the excess reagent. So we start this problem from the limiting and we go to the excess, where the heart of our problem is the want over given ratio. We have 1 mole of C2H4. Its molar mass was determined to be 28. Again, I have a 1-to-1 stoichiometric ratio. And now, of course, the molar mass of hydrogen comes out in our third step. Its molar mass is 2. 100 divided by 28 times 2 says that we've used 7.1428, so 7.14 grams. Along the way, we're consumed or used up. Remember how much we actually put in? We started with 15 grams of hydrogen. That was the initial amount given to us. We consumed 7.14. How much remained unused? Remember, I'm just going to like units so I can do an easy subtraction. 7.86 grams hydrogen in excess amounts. There we go. So start from the limiting, go to the excess. Make sure you go to the exact same unit as what you were provided with as the initial amount so you can easily subtract. We have one more in this particular set for practice test C. Let me skim down and read what we're doing next. I believe it's thermochemistry. Yeah, we got a beryllium metal reacting with some acid, hydrochloric acid, generating, liberating, releasing. All of those words are telling me exothermic, of 134 kJs of heat. We need to write a thermochemical equation, draw the enthalpy diagram, and use a little stoichiometry in the part C. Oh, let's go to work and see how easy this is becoming for us. So third problem says beryllium metal, so Be. Not that I have to, but I certainly will to include some extra practice with our states of matter adjective. Be is a solid. Reacting with hydrochloric acid, HCl. Its state of matter is aqueous. Do you recognize this pattern of change? Element with a compound where beryllium is going to displace that hydrogen. Beryllium and hydrogen exchange places. Molecular hydrogen sure forms, and we'd see evidence of change as those bubbles came out. Beryllium, when it goes into a compound, hooks by a +2. Chloride, when it's in a compound, hooks by a -1. So we get BeCl2. We can balance that equation by simply placing a 2 in front of the HCl. So a 1-to-2 to 1-to-1 balanced equation. Keep in mind, this is a perfect balanced equation, but it asked me to do a balanced thermochemical equation. That means I must include the delta H, the enthalpy of reaction, the enthalpy. It said it liberated, generated, released, gave off heat energy. Exothermic values are negative. It released 134 kJs of heat. So be sure that you've got this part included. I can't stress enough that without the delta H, I have to mark points down. The enthalpy diagram simply is a nice XY axis that separates heat content. So I just label my Y axis as the heat content. Oh, you can be much neater. And that's a KJ, heat content. Exothermic reactions show the reactants at a higher energy state than the products. And the amount of heat that separates them is 134 kilojoules of heat. Do you have your labels on your y-axis, heat content? Your equation still remains balanced. We still point from reactants to the products. Reactants are up high, products are down low. The letter C. How many grams of beryllium? Let's put this under here so we can tabulate it. So we're being asked to solve how many grams of beryllium, so that's my want, must react to liberate 1,500 kilojoules of heat. So my given is the heat and I want beryllium. If I'm liberating, generating, releasing, that's a negative 1,500 kJs. This starts me right into the heart of my problem. I like to get my parentheses ready so I can see my target, which is grams of beryllium. Heart of my problem shows for every 1 mole of beryllium we use, what was that value? Negative 134 kilojoules of heat would be released. We need a molar mass for beryllium. Do you know that one by heart? Let's find it. You're probably much faster. Molar mass of beryllium. Let's say 9.01. See it right there? 9.01. You probably rounded to 9. So I had to look that up. I didn't know that one by heart. So 9.01 or just simply 9. So notice what's happened. Our kJ's canceled, the mole unit canceled, and we've arrived at our answer. So negative 1,500 divided by negative 134 times 9. 100.746, I want to say 100.8 grams of beryllium would be needed to give off 1,500 kilojoules of heat. I feel your A+ coming on test day.